Welcome to Lesson 6.2 Direct Reference Optimization DPO Overview. You've learned how to make a model capable. Now you're going to make it good in the moral sense of the word. Direct reference optimization is a technique for teaching a language model which responses humans actually prefer. More helpful, less harmful, more honest. And the remarkable thing is that it does this without any reinforcement learning at all. This lesson runs about 90 minutes and sits at the advanced end of the difficulty scale. But by the end, you'll have a genuinely aligned model running on your own hardware. Learning objectives. Here's what you'll walk away with. You'll understand how DPO differs from the older RLHF approach and why that difference matters for you specifically. You'll know how to build a human preference dataset, run a DPO training loop, and evaluate whether your alignment actually improved. You'll also develop an intuition for the tension between helpfulness and safety, and how to iterate your way to a balanced model. What is DPO? Here's the problem DPO is solving. A model fresh off supervised fine-tuning knows a lot, but it has no sense of judgment. It might give you a verbose non-answer when you needed 3 bullet points. It might repeat a harmful claim it saw in training data. It might confidently invent a fact it doesn't actually know. The traditional fix for this is RLHF, reinforcement learning from human feedback. You train a separate reward model, then use a policy optimization algorithm like DPO to nudge the language model toward higher reward outputs. It works, but it's a 3-stage pipeline that's notoriously unstable and requires serious compute. DPO collapses all of that into a single supervised training step. No reward model, no RL loop. You give it preference pairs, one good response, one bad response, and it learns directly from the contrast. Simpler, faster, and stable enough to run on your Tesla P40S. The comparison is stark. RLHF involves 3 training stages: an unstable RL loop, slow iteration, and the kind of hardware budget that only large research labs can justify. DPO is 1 stage, supervised training, fast, and runs comfortably on consumer-grade GPUs. Quality-wise, both approaches reach excellent alignment. The difference is entirely in cost and complexity. For everyone outside a major AI lab, which is you, DPO is the right tool. DPO training data format. Every DPO training example has exactly 3 fields: a prompt, a chosen response, and a rejected response. The model learns by seeing the contrast, what good looks like next to what bad looks like for the same input. The format is straightforward JSON, and understanding it deeply is worth your time because the quality of these pairs is the single biggest lever on your final model's behavior. The base structure looks like this. A prompt key holds the user's question. A chosen key holds the response you want the model to move toward. A rejected key holds the response you want it to move away from. That's the entire contract. Everything else in DPO training flows from this 3-field structure, so make sure your dataset builder produces exactly this shape before you touch the trainer. Here's a concrete helpfulness example. The prompt asks how to install Python on Windows. The chosen response walks through the exact steps: download from python.org, run the installer, and, critically, check the Add Python to Path checkbox. The rejected response says something vague like, download it from the website and run the installer. Both answers are technically correct, but only one is actually useful. The model learns that specificity and actionable detail are what good means for this category of question. Here's a safety example. The prompt asks for advice on something illegal. The chosen response refuses clearly, explains why it can't help with that specific request, and redirects toward a legitimate alternative. The rejected response goes along with the request and provides the harmful information. Notice the structure of the chosen response. It isn't just a flat refusal. It maintains helpfulness by offering a legal path forward. That nuance matters because a model that just says, "I can't help with that" to everything has learned the wrong lesson. Here's an honesty example. The prompt asks, "Who won the 2024 World Cup?" The chosen response acknowledges the model's training data cutoff and explains it can't reliably answer questions about recent events. The rejected response confidently names a winner, which is a hallucination. This way teaches the model that admitting uncertainty is better than fabricating an answer. That's a genuinely hard lesson to instill through supervised fine-tuning alone, which is part of why DPO is so valuable. Creating DPO datasets. The highest quality approach is writing preference pairs by hand. It's slow, budget 2 to 5 minutes per pair, but every example is exactly what you intended. This method is best when you have a specific alignment goal and you need the model to learn a precise behavior. For most production use cases, you're targeting 200 to 500 pairs as a starting point. This Python snippet builds a handcrafted preference dataset and saves it to disk. Each entry in the list is a dictionary with the 3 required keys: prompt, chosen, and rejected. Once you've defined your pairs, the code writes them to a JSON lines file, one JSON object per line, named dpo_train.jsonl. The JSONL format is important here because it lets the dataset loader stream examples one at a time rather than loading the entire file into memory. The final print statement confirms how many examples were written, giving you an immediate sanity check before you move on to training. When writing hundreds of pairs by hand isn't practical, you can use a capable model like GPT-4 to generate them for you. The prompt you send should specify exactly what you want: a set of preference pairs covering helpfulness, safety, and honesty, with the chosen response demonstrating the target behavior and the rejected response demonstrating the failure mode. Ask for JSONL output so the results slot directly into your training pipeline. The critical step that people skip: review every generated pair before training. AI-generated preference data can be subtly wrong: a chosen response that's actually harmful, or a rejected response that's actually fine. Your judgment is the quality filter. If you've deployed a model and collected user feedback, thumbs up, thumbs down, ratings, you're sitting on a preference dataset you haven't mined yet. This function, create_preference_from_logs, converts conversation logs into DPO pairs automatically. For each log entry, it checks the feedback signal. A thumbs up means the actual response becomes the chosen example, and the function generates a deliberately worse version as the rejected counterpart. A thumbs down flips that logic. The actual response becomes rejected, and a better version is generated as chosen. The output is a list of properly formatted dictionaries, ready to merge with your manually created pairs. Real user feedback is some of the most valuable alignment signal you can get. It reflects actual failure modes in production rather than hypothetical ones. Training with DPO. Mathiapio, Viamitsoka. Before writing any training code, you need one additional library. Run this in your terminal to install Cold with its DPO dependencies included. The extras flag ensures you get the DPO trainer class and all its supporting components. Without it, the import will fail later. The installation takes about a minute, and you'll see pip resolving and downloading a handful of packages. Once it completes without errors, you're ready to wire up the trainer. This is the full DPO training script. Walk through it in layers. First, it loads your base model, the one you already fine-tuned with SFT using Unsloth's fast language model, with a 2048 token context window and 4-bit quantization to keep memory usage manageable on your P40S. The existing LoRa adapters are preserved, so you're building on top of your previous work rather than starting cold. Next, it loads your training and validation datasets from the JSON-L files you created, printing counts so you can confirm nothing was silently dropped. The DPO config block is where the training behavior is defined: learning rate, batch size, beta, number of epochs, and then the DPO trainer ties the model, tokenasa, config, and datasets together. A single call to write single quote trainer.trainetsky starts the run. When it finishes, the model and tokenizer are saved disk. Notice that the config parameters here are different from your SFT run. That's intentional, and the next few segments explain exactly why. The first parameter worth understanding is the learning rate. DPO uses a learning rate of 5E5, about 4 times smaller than the 2E4 you'd use for supervised fine-tuning. The reason is that your model already has good general capabilities from SFT. DPO isn't teaching it new knowledge. It's making subtle adjustments to which behaviors it prefers. Large gradient steps would override the capabilities you've already built. Small steps let the preference signal accumulate gradually without destabilizing the model. The second parameter is beta, which controls how strongly the preference signal is applied. Beta is the DPO specific knob that determines how hard the model is pushed toward chosen responses and away from rejected ones. The standard value is 0.1, a moderate push that improves alignment without making the model rigid. Drop it to 0.01 and the preference signal is very gentle, which preserves more of the model's original diversity and creativity. Raise it to 0.5 and the alignment becomes much more aggressive, which can improve safety scores but risks making the model overly cautious or formulaic. Start at 0.1 and only adjust after you've seen how the trained model actually behaves. The third parameter is batch size, and DPO has a specific constraint here. DPO processes pairs, not individual examples. For every training step, the model sees a prompt, its chosen response, and its rejected response simultaneously, which means each example consumes roughly twice the memory of an SFT example. That's why per_device_train_batch_size is set to 2 rather than the 4 to 8 you might use for SFT. To compensate, gradient_accumulation_steps is set to 4, which accumulates gradients across 4 forward. The effective batch size is 2 times 4, which equals 8. You get the training stability of a larger batch without the memory cost. The fourth parameter is the number of epochs. 3 epochs is the sweet spot for DPO. Unlike SFT, where more training generally means better task performance, DPO has a failure mode called over-alignment. The model memorizes the specific preference pairs so thoroughly that it loses flexibility on inputs it hasn't seen. 3 passes through the data gives the model enough exposure to internalize the preference signal without locking it into rigid patterns. Watch your validation loss during training. If it starts climbing while training loss keeps falling, that's the over-alignment signal, and you should stop early. Evaluating DPO alignment. Evaluation for DPO is fundamentally comparative. You need to see both the base model and the DPO aligned model respond to the same prompts side by side. This code loads both models using unsloth, calls for_inference on each to put them in generation mode, and then runs a compare_models function that sends the same prompts through both and prints the results. Pay attention to the generation parameters. max_new_tokens caps response length, and temperature controls randomness. Use consistent values for both models so any difference you see is from the alignment training, not from sampling variation. The prompts you choose for evaluation should deliberately probe all three alignment dimensions: helpfulness, safety, and honesty, so you get a complete picture of what changed. After successful DPO training, you should see four concrete improvements. Responses to factual questions become more structured and detailed. Requests for harmful content get refused cleanly with a redirect to something legitimate. Questions about recent events or uncertain facts get honest acknowledgments of the model's limitations. And importantly, the model should remain creative and genuinely helpful on normal requests. If it's refusing things it shouldn't, or hedging on everything, your preference data is out of balance. For a systematic evaluation, score your model across four dimensions: helpfulness, safety, honesty, and creativity, each on a 1 to 5 scale for a maximum of 20 points. Helpfulness measures whether responses are detailed and actionable versus vague. Safety measures whether harmful requests are refused appropriately. Honesty measures whether the model admits uncertainty rather than hallucinating. Creativity measures whether it remains engaging and flexible on open-ended tasks. Run this evaluation on both your pre-DPO and post-DPO. An improvement of 3 or more points on the total score is a strong signal that your alignment training worked. If a specific dimension didn't improve, that tells you exactly which category of preference pairs to add in your next iteration. Balancing alignment goals. Think of alignment as a triangle with 3 vertices: helpful, harmless, and honest. Your model needs to live somewhere inside that triangle, not at any single vertex. A model that's been trained purely for safety sits at the harmless vertex and refuses everything remotely sensitive, which makes it useless. A model trained purely for helpfulness will comply with requests it shouldn't. A model trained purely for honesty says, "I don't know," so often it becomes frustrating. The goal of DPO is to find the interior point, a model that's genuinely useful, appropriately cautious, and transparent about its limits all at once. The trade-offs are real and worth naming explicitly. Lean too hard on safety pairs and your model starts refusing reasonable requests, a phenomenon sometimes called over-refusal. Lean too hard on helpfulness pairs and you end up with a model that's compliant in ways it shouldn't be. Lean too hard on honesty pairs and every response comes with so many caveats it's exhausting to read. The composition of your preference dataset is what determines where your model lands in that triangle, which is why the next section on dataset weighting matters. Here's a concrete weighting scheme that works well as a starting point. Allocate 50% of your preference pairs to helpfulness, detailed answers versus vague ones, structured responses versus rambling ones. Allocate 30% to safety, appropriate refusals versus harmful compliance. Allocate 20% to honesty, admitting uncertainty versus hallucinating. For a 500 pair dataset, that translates to 250 helpfulness pairs. 100. These weights aren't sacred, they're a calibrated starting point. Your first training run will tell you where the model is still falling short, and you adjust the mix accordingly. Iterative DPO refinement. Y, C, V, Z, Linhanter, Cox. DPO training is not a one-shot process. The workflow is a loop. Train, evaluate, identify specific failure modes, add targeted preference pairs to address those failures, and train again. Your first dataset, call it V1, establishes a baseline. Your evaluation reveals which alignment dimensions are still weak. You add pairs that specifically target those weaknesses to create V2. Each iteration is faster than the last because you're not rebuilding from scratch. You're extending an existing dataset and continuing from an existing checkpoint. 3 to 4 iterations is typically enough to reach a well-balanced model. Here's what our realistic 3-iteration run looks like. Iteration 1. Train on 300 general preference pairs. Evaluation shows good helpfulness scores but poor safety. The model is still complying with requests it should refuse. Iteration 2. Add 100 safety-focused pairs and retrain on all 400. Safety improves, but now the model is over-refusing, flagging benign requests as harmful. Iteration 3. Add 50 pairs that show the model being appropriately helpful in situations that superficially resemble harmful requests but aren't. Train on all 450 pairs. The result is a balanced model. That progression, general foundation, targeted fix, calibration is the pattern you'll use repeatedly. Complete DPO workflow notebook. Save this notebook to notebook/05-advanced-techniques/02-DPO-alignment.ipnb. It contains the complete end-to-end DPO workflow in a single file. The first cell handles imports, fast language. The second cell loads your pre-trained model and tokenizer, applies LoRa adapters for memory-efficient training, and prints a confirmation. The third cell loads your JSON-L datasets and reports the pair counts. If those numbers look wrong, stop here and fix the data before continuing. The fourth cell defines the full DPO config with all the parameters covered in this lesson. Learning rate 5E5, beta 0.1, batch size 2, gradient cumulation for 3 epochs. The fifth cell instantiates the DPO trainer, starts training, and saves the result. The final cell runs a set of test prompts through the aligned model so you can immediately verify the behavior changes you were targeting. DPO training checklist. Before you call a DPO run complete, work through this checklist. On the dataset side, confirm you have 200 to 500 preference pairs. Verify the helpfulness, safety, honesty split is roughly 50-30-20, and spot check a sample of pairs to make sure the chosen responses are genuinely better than the rejected ones, not just longer. On the training side, confirm your loading from your SFT checkpoint rather than the base model. Verify the learning rate is 5E5. Beta is 0.1, and batch size is 2 to 4, and confirm training loss decreased across all 3 epochs. On the evaluation side, run the comparative evaluation against your pre-DPO model, confirm improvements in at least helpfulness and safety, and verify creativity scores didn't collapse. Save the final model and tokenizer before closing the notebook. Key takeaways. 7 things to carry forward from this lesson. DPO eliminates the reward model and the RL loop. It's one supervised training stage, full stop. The quality of your preference pairs is the dominant factor in alignment quality. Use a learning rate of 5E5, significantly lower than SFT. Beta at 0.1 is the standard starting point. Adjust only after you've seen how the model behaves. Aim for balance across helpfulness, safety, and honesty. A model that excels at only one of those is a worse model overall. Expect to iterate. 2 or 3 rounds of train, evaluate, refine is normal, not a sign something went wrong, and your Tesla P40s are more than capable of running this entire workflow. What's next? You now have a model that's not just capable, it's aligned. It knows what good behavior looks like because you showed it explicitly hundreds of times. The next lesson takes you deeper into the LoRa side of the stack. Lesson 6.3 covers advanced LoRa techniques, rank selection strategies, adapter merging, and squeezing more performance out of the same hardware. See you there. Additional resources. If you want to go deeper, the original DPO paper by Rafilov and colleagues is the primary source. It's readable and the math is well motivated. The TRL library documentation covers every parameter of DPO trainer in detail. Anthropic's constitutional AI work is worth reading for a different angle on the same problem, and the broader alignment research literature, particularly work from Anthropic and DeepMind, will give you context for where DPO fits in the larger picture of making models safe and useful. This diagram shows the two pipelines side by side, and the contrast is clarifying. The DPO pipeline is 3 boxes. Start with your SFT model, generate preference pairs, apply the DPO loss function, arrive at an aligned model. The RLHF pipeline is 5 boxes with a feedback loop. Start with your SFT model, train a separate reward model, run a PPO optimization loop that cycles repeatedly, and eventually arrive at an aligned model. Both pipelines end at the same destination. The DPO path just removes 2 entire stages, the reward model and the RL loop, and replaces them with a single loss function. That's the core insight of the rough file of paper, and it's why DPO has become the standard approach for teams without massive compute budgets. This diagram shows a concrete preference pair and makes the quality bar tangible. The prompt asks for a 2-sentence explanation of gradient descent. The chosen response is precise. It names the loss function, describes the direction of parameter movement, and mentions the learning rate as a hyperparameter, all in 2 clean sentences. The rejected response is the kind of answer a model gives when it's not really trying. It's how neural networks train by moving weights around. Technically not wrong, but useless. When you're writing your own preference pairs, use this as your mental benchmark. The chosen response should be something you'd be proud to show a colleague. The rejected response should be a realistic failure mode, not a straw man. This diagram shows what's actually happening inside the DPO training loop. At the top, your preference dataset feeds in. Each example is a triple of prompt, chosen response, and rejected response. 2 model instances are involved: the policy model, which is the one being trained, and the reference model, which is a frozen copy of your SFT checkpoint. Both models score the chosen and rejected responses by computing log probabilities. The DPO loss function takes those 4 numbers: policy log prob of chosen, policy log prob of rejected, reference log prob of chosen, reference log prob of rejected, and computes a scalar loss that measures how much better the policy model is at preferring chosen over rejected relative to the reference. The gradient update then pushes the policy model to widen that gap. The reference model never changes. It's the anchor that prevents the policy from drifting too far from the original SFT behavior. This chart compares DPO against several related preference optimization methods: RLHF, GRPO, IPO, and KTO across 3 metrics: win rate against SFT, training time, and stability score. The key pattern to notice is that DPO and RLHF achieve comparable win rates, meaning they produce similar alignment quality, but DPO's training time is substantially lower and its stability score is consistently high. GRPO, IPO, and KTO show lower win rates in this comparison, which reflects the fact that they are designed for more specialized scenarios. For your use case, aligning a fine-tuned model on your own preference data on your own hardware, DPO hits the best combination of quality, speed, and reliability on this chart. This slide shows the DPO loss function, and understanding it conceptually will help you debug training when something goes wrong. The loss computes the difference between 2 ratios: how much more the policy model prefers the chosen response over the rejected response, compared to how much the reference model preferred that same pair. The beta term, typically 0.1, is the KL regularization strength. It controls how far the policy model is allowed to drift from the reference. A larger beta means the loss penalizes drift more heavily, keeping the policy model closer to the original SFT behavior. The sigma is a sigmoid function that normalizes the whole expression into a probability-like value between 0 and 1. When training is healthy, this loss should decrease steadily. If it plateaus immediately or oscillates, check your preference pairs first, and consistent labeling is the most common cause. This slide covers the annotation process for building preference datasets at scale. The workflow has 6 steps. First, collect at least 500 diverse prompts that represent the real distribution of queries your model will face, not just the easy cases. Second, generate 2 to 4 candidate responses per prompt, ideally from different model checkpoints or sampling temperatures to get genuine variation. Third, have annotators select the chosen response using a consistent rubric. Score each response on helpfulness, accuracy, safety, format, and conciseness. Fourth, resolve ties by majority vote and discard near tie examples. Pairs where the margin is less than 1 point aren't teaching the model anything useful. Fifth, format everything as JSON-L. Sixth, apply a quality filter to remove pairs where the chosen and rejected responses are nearly identical. Either response is too short to be meaningful or there are formatting errors. The filter step is easy to skip and expensive to skip. Low quality pairs actively hurt alignment. These two charts are what healthy DPO training looks like, and you should keep them in mind when monitoring your own runs. The left chart shows the DPO loss curve. It should trend consistently downward across training steps, with no major spikes or plateaus. A flat loss from the start usually means your learning rate is too low or your preference pairs are too inconsistent. The right chart shows implicit rewards. The green line for chosen responses should trend upward, meaning the model is assigning increasingly higher probability to preferred outputs. The pink line for rejected responses should trend downward toward negative values, meaning the model is correctly discounting the bad responses. The gap between those two lines is your alignment signal. A widening gap means training is working. If the lines converge or cross, something is wrong with either the data or the hyperparameters.